Welcome back. This is the day the Lord's made. Let your rest be glad in it. In this video, I'm going to talk about chemical kinetics, which basically is the idea of like how fast reaction takes place, as well as half-lives, which again are really important because that's how oftentimes things are dated based off how long something's been reacting and how much you have now and how much they expect to have later. So anyway, chemical kinetics, this is just a basic idea that, when you think about kinetics, you think about motion, things moving, a process occurring. So kinetics is the idea of like how fast will a chemical reaction take place. So this is related to equilibrium, but it is not the same thing. So equilibrium is the idea that there's a balance point between products and reactants. The equilibrium constant has nothing to do with how fast the reaction takes place. So there could be like an equilibrium reaction constant that's like really large, which means that we favor the products, but it might be super slow. All right, so chemical kinetics deals with how fast it takes place. The rate of the reaction does not dictate what the K constant is, though, for the reaction as far as equilibrium constants. So do take note of that. So there are some things that can influence how fast reaction takes place. So in general, the factors are things like pressure, concentration, temperature, catalysts, and inhibitors. These are all things that can influence how fast reaction takes place. So if there are gases present, the reaction goes faster if there's more pressure, because the pressure is going to cause the gases to come closer together. So if we pressurize a gas container, the gas molecules inside will react faster. So that means a higher chance of reaction, which means a faster overall rate of reaction. If anytime concentration goes up, we expect to have a faster reaction. So the higher the concentration, the faster the reaction, because there's more to react. Temperature plays a big role too, because if there's more energy, then the molecules hit each other with more energy, and the chance of them reacting goes up, as well as there's enough energy to break the bonds. We're warm-blooded, as humans, so the temperature our body's at are very important for how fast reactions take place. This is also why we have a fridge. A fridge slows down reactions, so when you put food in the fridge, it doesn't stop the food from rotting, it just slows the process. It just slows the bacteria from rotting it, so it lasts a little bit longer. Again, a general rule is every 10 degrees Celsius is approximately twice the rate for most biological and chemical reactions. Other cool things too for like temperature, like when you have a fever, your fever is because your body itself is increasing its temperature. You have these pyrogens in your body, which cause your body's temperature to rise, because your body, when it fights off an infectious disease, it's using its white blood cells, which fight through chemical warfare. And your white blood cells kill faster if the temperature is warmer, because at higher temperatures, the reactions take place faster. And so the white blood cells are more efficient killing machines when it's warmer. And so your body gives yourself a fever to help the white blood cells out. So also things that can influence rates of reaction are things like concentration and surface area. A large surface area means more locations for the reaction to take place. So, because then they can mix together, like gases react a lot faster than solids, liquids, because gases are mixed in with everybody, but liquids and solids, they only make contact at the surface, so they're very slow reactions. So there's also things like catalysts and inhibitors. We'll talk about this more in greater detail for reaction mechanisms, but a catalyst is something that can speed up the reaction. It just makes it faster. Inhibitors are anything that can slow down a reaction. So inhibitors are things that will get in the way to stop the reaction. So teachers, parents, these things tend to be catalysts to make you get work done faster. Your cell phone, any video games you have on there, probably inhibitors slowing you down. So also things too can be just the conditions as well. Like, we already mentioned temperature, pH of the blood, that can have a big influence on how fast reaction takes place too, because it can make the proteins become denatured and slow down reactions that way. Concentration of chemicals in blood, huge impacts on how our body takes place. So anyway, these are just general things which influence how fast reaction takes place. A lot of times we're concerned about the math part of it, which is the idea of like, well, how fast do they react relative to one another? So how fast are we using X and how much faster are we consuming Y and how fast are we producing Z? So this is really just stoichiometry though. This is just saying that, hey, the rate of the reaction depends upon the coefficient. How many of these things here? So we can think of it in terms of our favorite chemistry equation, making s'mores. 2 graham crackers, 1 marshmallow, 4 chocolate pieces makes 1 s'more. And so if we know the rate of consumption for the graham crackers, we also know the rate of production for the s'mores as well as the consumption of these things too. Again, a real life example of this is when you think about taking inventory, if you're like a big manager or something, you really just have to keep track of like some of the major pieces, and then you know the rate of the other ones being used as well. So, if you're making cars, or some other big machine and has, it's easier to count how many tires you have than how many screws you have, when you're making something. And if you know the rate at which you're using the tires, you know the rate that you're using screws as well, because there's a ratio between them. And so you just got to keep track of the big pieces, and then you'll know how fast the little ones are being used as well. So in this example, let's say that we're consuming 10 graham crackers per minute. How many s'mores are we making per minute? We just set up a ratio. Well, since the ratio here is 2 graham crackers makes 1 s'more, and we have 10 graham crackers, 10 divided by 2, that'd be saying we have 10 graham crackers, uses 2, and every single time we use 2 graham crackers to make a s'more, how many s'mores are we making? We've been doing this since early this semester. We would see that that is 5 s'mores per minute. Now, you should note that when we're talking about rates of chemical reactions and connecting to like production and consumption, by convention, we make negatives on the reactant side. So we would say like negative 10 graham crackers a minute because it's a reactant, and we'd say positive 5 graham crackers a minute because it's a product. Real life again here, combustion of propane, and this is actually real relevant for like your car engine. It doesn't use propane, but the general idea is the ratio between oxygen and the fuel inside the pistons is really important. If you have too much fluid, too much of your gas, you're going to flood your engine, and that's bad because your engine won't run. If you have too little of the fluid and too much of the oxygen, if you have the wrong ratio, then you're going to lean and your car engine doesn't have any power. And so the rate at which they pump in the fluid should be proportional to the amount of oxygen coming into the engine. And so again, one way to increase your fuel efficiency for your vehicle is just to change your air filter or clean it out. That way you can have better airflow into it. We should also mention your car gets better gas mileage when it drives faster as far as the engine is concerned, because it's able to get more oxygen into the engine. In any case, so here we have, it says 1 propane reacts with 5 oxygens. How much CO2 and water is we produce? And we're given the rate. Let's say that we're consuming -4 moles per minute for the propane. So per minute, we're using 4 moles of this. What's the rate for the other guys here? So if we just keep track of this one here, we know the rate of the other ones as well, because we can just use our stoichiometry ratios. We know that 1 of these uses 5 of these. So if we're using 1 of these, 5 of those, we proportion up. Well, how much would 4 of these require over here? If we had 4 of these being reacted, how many of these need to be 5 times as much? So we'd have -20 moles of oxygen being used per minute. So if we had -4 for the propane, it'd be -20 for the oxygen. And since every one of the propanes makes 3 CO2s, it's 3 times as much carbon dioxide. The only thing different I'm saying, instead of doing a negative, I'm making a positive. We're producing the carbon dioxide. So -4 per minute means 12 CO2s per minute as a positive as a production. And for the water, 4 times as much water, because it's 4 waters for every one of these. So 4 times the -4, but making a positive because it's a product. So this is the general idea for doing stoichiometry when it comes to reaction rates. Again, why it's important? Because usually you just keep track of one thing and then you know the rate of everything else. If you can't keep track of something else's rate, you just keep track of the big thing. All right, so moving on to another one we care a lot about, which is half-lives. Half-lives we care a lot about because people use these to date things. Now, I do not agree with the half-life ages they've come up with concerning the age of the Earth. I believe the world is less than 10,000 years old. It is a young Earth, and it's decaying quickly. The reason that I don't agree with that is because I believe there are some faulty assumptions that have been made, meaning that we basically don't know how much was there originally. Now, the actual science behind half-lives and the process is good science, but the philosophy of the old age is bad because we don't know those things. But that's a longer conversation at a different time. So what you're concerned about is how to solve a half-life kind of question. So first off, let's start with the idea of what a half-life is. It just is how long it's going to take for the concentration to halve. So uranium is radioactive, at least some of them. So if we have 1,000 radioactive uraniums, how long would it take for them to be half that, 500? That's the half-life, the time it takes to do that. We'll talk about rate orders later, but for now, it's enough to assume that, it's safe to assume that in this chemical reaction, it's only based upon just the uranium. There's nothing else influencing it, so it's only dependent upon its concentration. So if you have twice as much uranium, you get twice the rate. If you have half as much uranium, you have half the rate. Therefore, we have this uniform decay that's easy for us to figure out the rate or how long it's been decaying for. We're going to do this, and you might have solved this other ways in your math class. In this class here, I'm going to teach it using these two equations here. So first off, this equation here on the bottom. This is just a magic number, the 0.693. If you take 0.693 divided by, this is not the same as the equilibrium constant. This K constant is just for the chemical kinetic, the rate of the reaction. Divided by the rate of the reaction constant, you get the half-life. Again, this is just a magic number. So also, if you take 0.693 divided by the half-life, you can get the K constant just doing a little algebra. This equation here is an equation that lets us figure out how much we have at different times based off the time. So the NT, this is how much we have currently. So after X amount of time, how much do we have of the radioactive substance, or how much we have of the material. The N with the notch here is the initial concentration. This K, again, is the K constant that goes down here as well. This is the same K. That's just how fast it is. So the bigger the K, the faster it decays. And the T is going to be how long it's been. This T is different than this T down here. This T is the actual time. This is just the half-life time. And so it makes more sense to do a couple samples to show you how this works. So for example, here are a couple questions for us. Let's say a student wants to find the half-life of a new substance they discovered. Good for them. They're going to be famous, probably on the periodic table. So let's say they had 120 grams of substance, and 32 days later, they're down to 12 grams of the substance. And wants to know the half-life of the substance. So we are going to be looking for the half-life, which is going to be the T1 half here. We are given the initial amount and the final amount and the time that the experiment took place. So we have the NT, the N naught, and we have the T over here. We don't have the K. We're going to solve for the K, and once we solve for the K, we can come back to this one and actually find the half. So again, we're going to do this in 2 steps. We're looking for the half-life. We know the initial, the final, and the time. We're going to use the first equation first to solve for K, and use the second to solve for the half-life. Do note this log, but this is natural log. So watch out on your calculator. You actually have 2 log buttons. You have one that's log. That is a base 10 log one. Don't use that one. You're using the natural log one, ln. So it's under calculator. It has a capital L, lowercase n, or it might be capital L, capital N. But it's also the button which has the EX generally. So also, you should know that my daughter's initials are named after this button on the calculator. She is E natural log, so for population growth. So anyway, ln, so we're going to take natural log of how much we had now, which is we have just 12 at the end. The original was 120, so natural log of 12 over 120 equals negative K, which is some constant for the reaction, and then this here is the time, 32. Solving for K, K is this, 0.0719. That is the rate of the reaction. And since we did this with days, this K constant would be in terms of days too. So as long as you're doing the math, as long as it wants the time in the same aspects for both, so here we have days up here and we want days, then the K constant will be proper for you. So you shouldn't have to worry about unit conversion of this class. So once we get the K constant, we go back to the next equation, 0.693 again, which is just a magic number, divided by our K constant gets the half-life, and that tells us that our half-life is approximately 9.6 days. Now, a nice thing about this too is you can just double check your work without using your calculator, or you might still need to use it, but you can have an idea of what you expect. So 120 grams divided by 2, which would be like the first half-life, we'd have the concentration would be 60 grams up to approximately what we just calculated, that'd be 9.6 days. So if we keep following this, just math, we'd say, okay, well, divide by 2 again, that's another half-life. Now, because it's time it takes to halve again. So again, you'll see that the first time we lost 60, this time we lost 30. Why? Because as we have less, we react slower. So that's what it means to be a first-order reactant. More on that later. But anyway, so after 19 days, we'd predict there'd be about 30 grams. After 28 days, we'd expect to be about 15. And after 37-ish days, we'd expect to be a 7.5. Now, we finished with 12, and 12 grams between 20 and 37. And we had 32 days. Our answer is reasonable. Another question. Item 131, used to treat patients with cancer. has a half-life of approximately 8 days. We give the patient a dose. How long will it take to be less than 25 milligrams? This is also useful science for like, when do you need your second dose if you're having chemotherapy or given some radioactive substance? Again, iodine 131 is very common. We give it to people because it's radioactive, and what happens is we give it to the person, it goes into the place we want it to go, it blows up, decays, and kills stuff around it. And so it's all it is just a bunch of math to know, well, how long will it take until the iodine is too little to do any more damage, and then we got to give you another dose to up it again. So, and this is real good science here. All right, we're looking for the time it takes the iodine to reduce to a certain concentration. We're given initially 500, 25. This time we're going to be solving for the actual time it takes, which would be basically like, okay, what if we want to give you another dose once it's less than 25? So when should you come back in? So we're going to use the second equation first here. We're going to use this one here because we were given a half-life actually. So we were given a half-life of 8 days. So we can take 0.693, which is a magic number, do a little algebra, solve for x. X turns out to be this number here. Then we can say, well, we gave the patient 500. We want to know when it gets down to 25. So 500 would be our original. 25 is how much we have now. Solve for the time. In this case here, it turns out to be about 34.6 days, which means we would tell the patient, come back in 5 weeks, we'll give you another dose. All right. Godspeed. Have a great day.